Alrighty, so I don't know exactly how I said I was going to progress. There's 1,000 different ways that you can do this, and I have to figure out how best to do it by chopping it up into 15 to 20 minute chunks. So here's what we're going to do. We're going to enter into a discussion of left hand, right hand, and midpoint by going through another example. And here's the scenario that we're going to be dealing with. Okay, we want to talk about f of x is equal to x squared plus 1 on the interval 0 to 2, and let's go 4 subdivisions again. Okay. Now, I just so happen to have, again, gone ahead and drawn this a couple of times. I'm a little bit worse with a pen than I am with a pencil, so sorry about the messiness of the graph. But that's basically y is equal to x squared plus 1. And we're looking from 0 to 2. And now notice that I've changed the scale, and I've done so that we can actually see the outputs all the way to 5 at 2, but so that we can actually sort of play with these subdivisions here, so I've sort of stretched out the x interval, and that's why it doesn't look quite as steep as it usually does. Now let's go ahead and let's look at left-hand Riemann sum for x squared plus 1. Again, I think it's a good idea to go ahead and draw it. Now we know that if we're looking at 4 subintervals and we're going over 0 to 2, I know that delta x, and remember this is something that I introduced last time, b minus a over n, which is basically just saying it's the width of the interval divided by the number of subintervals gives you the width of each subinterval. I mean, that actually basically, you know, I wouldn't memorize the formula so much as just understand that that just makes intuitive sense. Now, that means that each of our subintervals is going to be half a unit wide. Okay, and so that's our delta x. That's part of our notation as we move forward. I'm going to introduce a little bit more, likely towards the end of this video, perhaps in the next. There's our 4 subintervals, 0 to 1/2, and we'll go ahead and put the half in there, and we'll go ahead and put the 3/2 into there so we can actually see those subintervals. Now, I want a left-hand Riemann sum. So the left-hand side is going to be the thing that determines the height of the subinterval. Okay? And again, because this is increasing, a left-hand Riemann sum is going to give us an underestimate. That just kind of makes sense, right? Because from left to right, it goes up. Yeah, that should, again, make intuitive sense. Now, we simply need to go ahead and figure out the area of these 4 rectangles. Now, I know that the common width is 1/2. So actually, I could go ahead and factor those out, right? I could factor the 1/2 out and then just put a sum of all the heights. Because then if you were to distribute that 1/2 across, you would get 1/2 times this height, 1/2 times this height, 1/2 times this height, and 1/2 times this height, which would give you the 4 different areas, right? So I know that it's 1/2, and then it's going to be f of 0, right? It's going to be f of 1/2, it's going to be f of 1, and it's going to be f of 3/2. Those represent the 4 left-hand sided outputs for that function from 0 to 2. Okay? Now, I happen to know, and squaring and then adding 1 is relatively easy. So you get 0 squared plus 1. You get 1/2 squared, which is 1/4, plus 1. You get 1 squared plus 1, which is 2. And then you get 3/2 squared, which is 9/4, plus 1, which is 13/4. Okay? And actually, that's going to wind up being a nice, neat, rational number. Now, I know that if I add 5/4 and 13/4, that's 18/4, or 9/2. 9/2 plus 3 is 9/2 plus 6/2. Follow? So 9/2 plus 6/2 is 15/2 times 1/2 is 15/4. That is our left-hand Riemann sum from 0 to 2 with 4 subintervals of y is equal to x squared plus 1. Okay? Now, I need you to focus right here because this is going to be important. It's important that I actually put that step in here because we're doing it in the very specific, but remember, what we always do is we go from the specific and we go to the abstract, and that's coming down the pike here in just a moment. But in the meantime, let's go ahead and do the right-hand Riemann sum, okay? The right-hand Riemann sum, we're still going to be chopping it up into 4 subintervals, okay? So let's go ahead and do that, and let's go ahead and put the 1/2 and the 3/2 in there as well. So I know that I'm, having to, there we go. And of course, because this is increasing and we're doing right-hand Riemann sums, we know that it's going to be over estimates in terms of the area. Okay? And again, let's go ahead and, go ahead and color it in just so it makes a little more sense and we can actually see the fact that this is an overage because we see green that is not under the curve. We're trying to find the area under the curve. So if there's green that's not under the curve, then obviously that is a overestimate. Okay? So let's go ahead. We know, again, we're going to factor out the 1/2. Okay, and then instead of f of 0 being your first height, f of 1/2 is going to be your first height. And then f of 1, and then f of 3/2, and then f of 2. Okay, now let's go ahead and get values for those. We have 1/2, and we know that 1/2 squared plus 1 is going to be 5/4. We've already figured that out last time, right? 1 squared plus 1 is 2. 3/2 squared plus 1 is going to be 13/4. And 2 squared plus 1 is going to be 5. Now we remember that these two added together, the 5/4 and the 13/4 is 18/4 or 9/2. 9/2 and 7 is 9/2 plus 14/2, so that's 23/2. So that's 23/4. Now remember that the left-hand Riemann sum was 15/4. This is 23/4. So the left-hand Riemann sum was a little less than 4. And this is a little less than 6. So we know that the actual area is going to be somewhere between 15/4, which was an underestimate, okay, and 23/4, which was the overestimate. Okay, that's going to be very, very helpful. Now, oftentimes when we're doing this, we are not relegated to just considering the left-hand and the right-hand Riemann sum. There's also what's called the midpoint sum, and let's go ahead and look at that really quickly. Same function. I went ahead and did a third graph, but here's the thing. When I start dividing this up, I know that if I'm looking for the midpoint to determine, I'm looking for this point right here, halfway between 0 and 1/2, meaning at 1/4, to determine the height. I'm looking for 3/4 right here to determine the height. I'm looking for 5/4 right here to determine the height. And I'm looking for 7/4 right here to determine the height. And so what I have here is, if I go ahead, and remember this is just a rough sketch, so don't put too much import into what the values actually look like. We'll actually figure those out numerically here in just a second. And oftentimes a midpoint sum is going to be a better approximation because it kind of basically, there's a little bit of overage and a little bit of underage, a little bit of overage and a little bit of underage, a little bit of overage and a little bit of underage, a little bit of overage and a little bit of underage. And that winds up giving us oftentimes a better approximation. Okay, let's go ahead and fill it in green so that we can actually see the little bit of over and the little bit of under, and a little bit of over and a little bit of under. And they don't, you can't really just take this piece right here, right, and fit it right here. Because this is not linear, that piece of overage won't fit exactly into that underage, but it's close, right? That bit of overage won't fit exactly into that bit of underage, but it's close. And the same thing with these two, and the same thing with these two, okay? So what we're going to do, and the calculations here are a little bit more tricky, because what I'm doing is the same width, right? But it's f of 1/4, f of 3/4, f of 5/4, and f of 7/4, okay? Now that's going to wind up getting a little bit tricky because, you know, multiplying or squaring fractions just winds up being tricky, right? So I know that if it's 1/4, that's 1/16, right? So what you have here is 1/16 plus 1, and what you have here is 9/16 plus 1, and you have 25/16 plus 1, and you have 49/16 plus 1, okay? Now, you know, putting it like this instead of actually adding them together winds up helping you out just a little bit, because 49 plus 1 is 50, okay? And 25 plus 9 is 34. So 50 plus 34 is going to be 84. 84/16 plus, and then you add the 4 ones together, 4 times 1/2, okay? Now, here's the thing. 84 over 16 reduces, okay? They both have 4 in common, so you're going to wind up with 21/4, and 4 can transform into 16/4. That's 37 over 4, or 37 over 8 once you multiply it by 1/2. Now 37 over 8 is obviously just a little bit shy of what? Well, 37 divided by 8 is a little bit shy of 5, because 40 over 8 would be 5, right? And 36 over 8 would be 4.5, so this is basically 4 and 5/8. And that does fall between, okay? 15/4 is less than 37 over 8, which is definitely less than the 23/4 that we got for the other sum, okay? So this is the midpoint right here. And like I said, the arithmetic winds up being a little bit more difficult, but that falls between showing the fact that it is certainly going to be a better approximation and closer to the actual area, okay? Now, once we've done this, and you've been plugging in so many things for f, right? Because we have the left-hand Riemann sum, and what we plugged in for f was 0 and 1/2 and 1 and 3/2. And then we had the right-hand Riemann sum, and we didn't plug in the same numbers. We plugged in 1/2, 1 and 3/2 and 2. Okay, and then we basically plugged in 1/4, 3/4, 5/4, and 7/4 for this one. So oftentimes, in order to do notation, they want to sort of abstract from that and talk about it in general, okay? So a Riemann sum, and I'm going to reintroduce sigma notation right here. A Riemann sum, okay, is basically going to be sigma for I 1 to n, okay, and that will give you n subdivisions, right, because that'll give you n areas, delta x, and then whatever the function value is for the ith, and that's ith, right, for the ith subdivision. So this is the width, this is the height, and you're adding up that product from 1 to n times, okay? That becomes pretty important notation, okay? So x sub I basically winds up being sort of the catch-all notation for whatever it is that this particular scenario is asking you to plug in to your function in order to evaluate and have those outputs as heights, right? Because the output at those particular points are the heights of those rectangles that you're using to add them all up and approximate the area, okay? So now that we have that notation, we're going to go ahead and move on to some polynomial ones. And you remember that we basically we basically used the sigma notation to sort of churn out a couple of values, and then we took it even a little bit more abstract and started talking about formulas for the nth, for any n subdivisions for a particular scenario. And here we're getting very, very close to getting to actual area, but we'll pick up a little bit more on that in the next video.